Thank you very much. So my name's Iain Russell. I work in the development section at ECMWF. And yes, like you said, we're going to spend some time just looking at the concepts of EarthKit, and then you're going to get some hands-on experience a little bit later. So first of all, just setting the context of EarthKit. I hope you can see the slides. So ECMWF has a long history of developing software in support of the NWP models, both in terms of this of operations, running them, and also helping users to access and process and visualize the data that comes out. These days we call this software ecosystem the ECMWF software engine. That's the collective name if you hear that phrase in the future. And a couple of years ago, we decided it was a time for a refresh in a way. We set a new sort of roadmap and strategy for how we're going to develop software in the future. We had a few sort of guiding principles that we sort of declared, things like doing open development, making smaller and more reusable software components rather than monolithic software packages, better use of third-party software and some integration with third-party software, and then the considerations that you'd need when you're working on today's modern hardware. And the result of that has been EarthKit. So EarthKit is a new set of high-level, scalable, interoperable Python components, each focused on a specific area. We intend them to be used both in operational services and also in research. So what's happening maybe in our sort of production operations, you can use something very similar in your sort of Jupyter notebook on your laptop. It's quite a nice time to be designing new software because fairly recently, with the upsurge in machine learning and GPU availability, we're able to sort of build that in as a first-class citizen into EarthKit. We know from the past that disk usage is often a bottleneck in performance, so we try and do as much in memory as we can, avoid the disk, and of course reduce boilerplate code so that people aren't writing the same basic things all the time. If you go into any of the GitHub repos for these components of EarthKit, you'll see they've all got a different sort of software maturity. They've all been started their developments at different times, so some are more mature than others. So have a look at that to see how comfortable you feel sort of taking that into your own systems. All the code is on GitHub, open development. We get issues and pull requests from inside ECMWF, outside ECMWF member states. It's been very collaborative. So the software stack, not a bad way to visualize it here. So our aim is that applications on the top level there are basically the users of EarthKit, things like EC charts you might be familiar with, the Copernicus data store, our post-processing software, our verification software, Quaver, for instance. These will all be users of EarthKit, and also researchers running their Jupyter notebooks on their laptops. Second layer shows the actual EarthKit components. So you can see we've got things like data, regrid, meteo, plots, and so on. So each Python package there is specific to a particular purpose. I'll go over those in a minute. They also sit on top of our more established libraries, such as EC codes. So if EarthKit data is doing something with GRIB data, for instance, it will be actually using EC codes under the bonnet. And it also gives us access to things like our FDB and Mars and our interpolation libraries and so on. And at the very bottom, we've got our third-party libraries like our Python packages, the standard NumPy, Xarray, Matplotlib, and so on, and binary libraries that we use, for instance, for compressing our data. So here is what the EarthKit ecosystem looks like just now. You can see it's nice and colorful. So I'm just going to say a little bit about each of these with a bit more emphasis on EarthKit data, just because that's, I think, the most central component to everything. So EarthKit data is for the format agnostic handling of geospatial data. It could be from local files on your disk or some local service, or they can be remote. I'll talk about that in a moment. So it gives you the facilities to access the data, inspect it, filter it, thread safe modification of the data. And the basic concept, this sort of abstraction of the data, is that of a field, which is a horizontal slice of the atmosphere. You've spent today looking at EC codes and GRIB, so you can think of that as a GRIB message, which is also a horizontal slice of the atmosphere, but of course NetCDF also gives you that kind of data. So a field is basically abstracted into a set of data values, the actual temperatures or whatever quantity you're looking at, plus the metadata, which looks quite like a dictionary. You can instantiate these from GRIB, NetCDF. One of the, I suppose, most basic ways of creating a field is just a NumPy array plus an actual Python dictionary of metadata. That's also a valid field. We combine these together into a list, which is what you get if you load a GRIB file, which is a list of messages. You get a field list in EarthKit data, which gives you access to those messages as fields. Once you have that, you can extract the data as NumPy, Pandas. You can convert to Xarray using EarthKit data's new GRIB to Xarray engine. We also have some support for non-field data, observation data from Buffer, for instance. You also learned about that today. We have other formats like ODB, CSV, coverage JSON. Largely, we don't have a particular structure we give these to you. We just give them to you as Pandas or Xarray for you to work with. So here's an example of what EarthKit data looks like. Chosen the example here of streaming data from an S3 bucket. So we're calling the EarthKit data from source. We are saying that the data source type is S3, and then the request is the specific details that you need to specify the data you want from the S3 bucket. And what's quite interesting is we have these nice little options here in the box, this stream and read all. So if stream is set to false, then EarthKit will download the data and write it into your temporary disk. If you'd rather avoid accessing the disk, then you can say stream equals true, in which case it's going to be read directly into memory. If this is some massive data set and you don't actually have enough memory on your machine to handle it all, then you can also set read all to false, in which case it's going to give you back an iterator, and each time you loop through the fields, it's going to retrieve another one or another 5 or however many you specify. So you can still get through all the data, but only so much of it will be in memory at one time. Or you can set read all to true, in which case it will download the whole lot at once into memory, if you can handle that. So this EarthKit data from source, just to reiterate, this first argument is how you specify the type of source. So we have the example here of your source being just a local file or a file on a URL. We've got the CDS there, we've got Mars, ECMWF Open Data. These are all valid sources where EarthKit can get its data. And in fact, if you go to read the docs, you'll find a whole bunch more. That's just a small subset. Other core component, I would say, is EarthKit plots. So this is a package designed to give you publication quality, weather and climate graphs and maps. It's can take NumPy, X-ray, and EarthKit data objects as input. It's built on top of matplotlib and cartopy, also with some plotly functionality. And what we add on top of that is domain-specific knowledge of meteorology and formats, and how we typically want our titles to be organized. There's a lot of graphical styles built in. The idea is that if you see some nice map on our website somewhere, you should be able to find this style that we used for that and just use it in a one-liner inside EarthKit plots. And of course, you can also add your own style libraries or just modify bits and pieces as you like. And generally reducing boilerplate on the amount of code that people have to write to produce useful meteorological plots. We've got EarthKit regrid. So this is where you want to transform data on one grid into another grid. Maybe an obvious example being we tend to produce data on a reduced Gaussian grid. Quite often software doesn't like that so much because it's not completely regular. So you want to put that in a regular lat-long grid. Certainly if you're doing machine learning, you might want to do that. So that's what EarthKit regrid is for. You can give it either EarthKit data objects or NumPy as its input. And I'll mention later, we're going to be incorporating our mere interpolation library into this, which will give it more power in the near future. EarthKit Geo is for geographical manipulations. These are things that are not specific to meteorology, but still useful within the domain. Things such as rotating points around a pool. EarthKit Meteor is for meteorological specific computations, things like thermodynamics, wind computations, vertical interpolations. Current interface is array input and output. Those arrays could be NumPy, it could be like torch arrays, GPU accelerated arrays. We are adding X-ray and EarthKit data support into there as well. A future release. EarthKit transforms is for aggregations in time and space. So for example, getting the daily maximum and that sort of thing. We also have EarthKit time, which is a little bit different. This one does not actually deal with data at all, but just date time objects. It's for creating sequences of dates and time manipulations, but it's not actually manipulating your data at all. We have a component dedicated to hydrology, EarthKit Hydro. So it's got a representation of river network objects, how values propagate across those networks. And then I think maybe the newest kid on the block is EarthKit Workflows, which is for defining and running task graphs. And then we've got EarthKit Utils, which is not really intended for end users to use. It's more shared components that the other EarthKit packages can use. So how is EarthKit being used today? Well, Our Anemoy machine learning framework is currently using it for data handling and plotting. Our post-processing suite is also using EarthKit for data and time handling and thermodynamic computations. Destination Earth, we're using it for retrieving and visualizing data via the Polytope engine, which is incorporated into EarthKit data. And then you'll see it in use in some Copernicus web applications, such as the C3S Global Temperature Trend Monitor is using EarthKit. If you ask to retrieve things like daily minimum temperature from the CDS, then actually EarthKit transformers will be used in real time to actually compute that before giving it back to you. And yeah, we recommend EarthKit as the way to actually retrieve data from the CDS. So just to give you an indication that EarthKit is very much a living and evolving project with lots of work going on just now. Some of the things we're working on at the moment is on EarthKit Regrid. We are incorporating this mirror interpolation library, which was developed at ECMWF. When we release that version, it will bring support for more grid types to EarthKit Regrid. It will allow us now to crop areas. I know that was one of the topics from this morning. How do you crop sub areas out of grid? This will allow you to do that. It'll give you more interpolation methods. Example, grid box average gives you conservative interpolation if you want to preserve precipitation values over the globe, and also enhanced missing value support. EarthKit Meteo, as I mentioned, only takes arrays just now, so we're working on getting it to work with X-arrays. Our new GRIB to X-array engine is constantly being improved. We currently have, and Paul mentioned this morning, we have one called CF GRIB at the moment, which does GRIB to X-array. The idea is that this new, more flexible engine in EarthKit data will supersede that. It's already in very good shape. We're just adding the last couple of pieces that will allow it to take over from CF GRIB. One very powerful feature we want to add to EarthKit data is maths operators on fields, so that you should be able to load, say, analysis data and forecast data and just do difference equals forecast minus analysis, and it'll do all the computations for you and put them into a new field list. Another big bit of work we have just now is making this whole format agnostic thing work nicely for metadata. Right now, we certainly have some of that working. Like if you go from GRIB to X-array and NetCDF, at least sometimes you'll get quite nice CF compliant metadata, but it's more than just the software behind it. So we're working on the software level with EarthKit data to get really format agnostic metadata. But I mean, you heard from Sebastian this morning. He and his team are also working with the WMO and with the CF convention people. There's a lot of data governance work in there as well to actually allow us to exchange metadata between the formats. So there's a lot of work going on there. EarthKit plots. This afternoon, you will be able to get your hands on the new time series function. I think it was released yesterday, so you'll get to be the guinea pigs for it. Also, EarthKit Plots is the first in-house plotting package we've had, which can do RGB composite plots. That's also a fairly recent thing to come out of it. So, take-home messages is that EarthKit is ECMWF's new set of Python packages for weather climate science. suitable for operations and research. Everything is on GitHub. We welcome issues and pull requests and discussions. All the packages are on PyPy, so you can install them individually, such as pip install EarthKit data, EarthKit regrid, EarthKit plots, EarthKit hydro, but we also have another package called EarthKit, which simply has dependencies on the most mature of those EarthKit software components, and gives you a set of those which have all been tested together in our CI. So you get a nice little environment just by installing EarthKit. On Read the Docs, we also have documentation for all these packages. And those of you familiar with our Magix plotting package, that was a C++ based package with a Python interface, which has been generating our plots for many years now, that we're working to replace that with EarthKit plots over the coming few years. And METView, first released in 1993, 32 years old now. That's very much like Magix, it's in maintenance mode. If you're familiar with METView, you could almost say that EarthKit is what you would get if you were to explode METView into its component parts, because METView has a lot of functionality, but it's a monolithic application written in C++. It's not very easy for people to contribute to it, but if you explode that apart, write it in Python, you've sort of got EarthKit. And we've definitely taken a lot of the spirit of METView and taken that into EarthKit. So before we start any practicals, are there any questions?
So there is one in the chat.
Yes. Do you advise to use EarthKit to directly read dissemination grid files? Is it faster than using the EC codes and picking the data inside the grib ourselves? Does this work fine with grib1 files? Right. Yes, no, yes. Yes, I think it's a good idea to use EarthKit to read the dissemination grid files. Why not? In terms of performance, it's not going to be faster than using EC codes because it's using EC codes underneath to read and decode the grid files. But it does provide a very convenient way to filter the data. If you have a workflow which already is using grib filter, then maybe EarthKit data doesn't give you much on top. It depends what you're going to do afterwards. If you're going to produce a new file with selected data, then EarthKit data and EC codes would be much the same. If you're going to go on and do something without writing to disk, then EarthKit data would be a bit faster because you don't have to write the result of the filtering to disk. And yes, it's as agnostic between grib1 and 2 as EC codes is. Mohammed, yes. Okay, welcome. When are you expected to start migrating from METView? Do you have tools to help with the migrations? Yes, so Mohammed, I think what I would suggest for the most part, I think the biggest thing that most people will be waiting for from EarthKit is the ability to support those maths operations between field lists. That's the kind of big thing that's missing just now. Once that's in there, then I think it's become seriously possible to start migrating. We don't have tools to do the migration. We don't have any tools planned. What I could suggest is that if you have METView macros, then we do have a tool built into METView to at least turn METView macro into METView Python. And then once you have Python, it's much easier to move over to EarthKit.
Great, thank you very much. Any more questions by anybody online? Raise your hand or open your microphone as well, that's no problem. Okay, I don't see any, but please continue to ask questions in the chat. So, Iain, will you be staying with us throughout whatever's planned next?
Yes, I will. I need to disappear for half an hour, but
yep, no worries.
But
so
I will be back.
You can answer in the chat.
But,
yeah.
So let me just. I'll move on to the next slide, but I think James will hopefully be able to show this again. So we're just about to move on to the practical now. This slide will come back, so you don't need to worry about it yet. What we're going to do is I'm going to hand you over to the very capable Sandor and James, who will introduce the notebooks we have. So they've written a selection of notebooks just for this training course, which you'll be able to look at and run in different ways and just play with EarthKit. I think we'll give you sort of 30, 40 minutes for that, or as long as you need, really. So I'm going to hand you over now to Sandor, who is going to tell you about the notebooks that he wrote, and he'll hand you over to James, and then you can start the practicals. Sandor.
Brilliant, thank you very much.
Yeah, hello, I just share my screen to talk about the notebooks.
Great.
So in the GitHub repo that I think you already used today, you will find an EarthKit subfolder with some notebooks we prepared. So I just go through the 3 notebooks I wrote, and I give it over to James to introduce his notebooks. So first one I want to show you is the ensemble one, which is basically kind of demonstration on how to use EarthKit components to generate typical ensemble data-related plots like stem plots, spaghetti, and so on. It contains a little bit of computation, but it's mostly about the plotting with a small exercise in the end. So the next notebook is called Grid. It's about inspecting various grid data with the various global grids. So again, it's showcasing how you can inspect the grids, what you can do with it, how you can visualize them, how you can do interpolation and so on. It contains 3 different grids: regular Athlon, Gaussian, reduced Gaussian, and the Hilpix grid, and with an exercise in the end. And the last notebook I wrote was about meteorological computation with group data. It shows how to compute potential temperature and wind speed from group data, and how to save the results and how to visualize it. Again, with an extra exercise in the very end. I just want to show you that in this folder, there's a solutions subfolder where you can find all the notebooks with all the cells executed and the solutions available there as well. So it's there for you. And now I give the word to James.
Thank you, Sandor. So I was going to take over this. Hopefully you can hear me.
Yes, we can.
We're trying to just swap the audio so we don't get too much echo. So let me just share my screen. Yep, so there's a couple more notebooks. So again, in the GitHub repository, I've put a link to the binder in the chat, and in a moment I'll reshare the slide that Iain was sharing with all the other details on how to run it on your own machine, and I'll copy some of those into the chat as well, so you can copy those directly from there. But just to mention the other notebooks that are available, there's one here also for comparing different data from different centers and different models. So there's one all about comparing the Met Office's HADCRITY 5 data with ECMWF's ERA 5 data set using EarthKit data, EarthKit transforms, and EarthKit plots. And then there's also one, as Iain mentioned, on the brand new time series features in EarthKit plots. So these are all a bit experimental. So we're very keen to get some users hands-on with this and see what they think. So there's an example called time series that's all about extracting time series data from ERA5 for a location, calculating some hourly data, so then calculating some daily statistics. And then there's a few exercises as well for you to follow on afterwards. So I'll just reshare that original slide, which I hopefully have in PowerPoint somewhere. Bear with me, sorry. Oh, it's the first time I've done this PowerPoint live thing. So hopefully that will give you.
Yes.
Okie dokie. So what I'm going to do is I'm going to go through this notebook on data from different sources. So as I said, this example is all about showing how EarthKit is designed to be data format agnostic as much as possible. This example shows you how to compare data from two different institutions, from two different sources, and in two different file formats without too much friction. So in this case, we're going to compare the ERA5 reanalysis dataset from ECMWF, which is available through the Copernicus Climate Data Store, with the HADCRUTI-5 global historical surface temperature anomalies from the UK Met Office. So this one's based on observations. So we should be able to compare the reanalysis dataset, which is sort of observations plus a model to try and get a good picture of the past climate against some actual observations of the past climate. So the components of EarthKit that we use in this example are EarthKit data for accessing the data sets, both the one from the Met Office and the one from ECMWF. EarthKit transforms to do some basic calculations. So we're doing aggregations in time. Namely, we're doing a climatology calculation and an anomaly calculation. And then finally, EarthKit plots to visualize our results. So if you manage to get EarthKit 0.13.1, you should find that you can just do import EarthKit as EK, and you get all of the EarthKit ecosystem in that one import. And one thing that we've actually released recently that's very powerful is importing EarthKit doesn't actually do anything at the moment of import. So it does what's called a lazy import. So some of these packages are very big and they've got lots of dependencies, but when you actually import EarthKit, all you're really doing is preparing your workflow for extracting the EarthKit components you need when you need them. So it's only when you actually call a specific component that it actually loads that component into your Python session. So in this example, we are doing a comparison of temperature anomalies for July 2024, so July last year, which was one of the hottest months on record globally. And as I say, we're going to compare ERA5 to HADCRUTI-5. So with ERA5, we are going to access the data from the Climate Data Store. So the Climate Data Store is one of the flagship products from the Copernicus Climate Change Service, which gives you free and easy access to a wide range of climate data sets. And ERA5 reanalysis is the most popular data set by a long way. And once you've signed up for a CDS account, and there are instructions on how to do that in the notebook, you can download data by selecting the data that you're interested in the download tab. So in our case, we're interested in monthly 2-meter temperature for 2024 July. And then at the bottom, I need to log in. Okay, go back again. There we go. At the bottom of the notebook, there's an API request, which shows you how to programmatically access this data. And EarthKit data gives you the ability to make a request to the CDS directly from EarthKit's interface. So we're doing EarthKit data from source CDS, and then we're passing the name of the data set and then the payload of the actual request. So for ERA5, this is the monthly average reanalysis, it's 2-meter temperature, and we're getting data from 1961 to 1991 so that we can calculate an anomaly. So this is our reference period for any of you familiar with how we calculate climate anomalies. And we're only interested in the month of July because we're plotting July 2024. And then, of course, we need July 2024 itself to to compare to our reference period to get our anomaly. Now, HagCruity5 is much more straightforward insofar as the Met Office has a dedicated website. So there's this website here which has the latest HagCruity5 data. So all I've done in this notebook is I've gone down to the ensemble mean, and then I've copied the link to this data. It's directly openly accessible through this URL, and then that's the link that I've put here. So just from this URL, we can go straight into EarthKit data. So we're doing an EarthKit data from source URL, passing that URL, and then we have that data in our EarthKit session. So then we're going to do a bit of data analysis on this. So in order to do that, we are going to convert everything to X-array. So for those of you who aren't familiar with X-array, it's essentially a hypercube package. It's sort of like NumPy arrays plus metadata in Python. So from the CDS, our ERA5 data is in GRIB format, but as Iain mentioned, we now have a powerful EarthKit engine which converts from GRIB to X-array. So if you have some data, it could be GRIB or NetCDF, whatever data you have in EarthKit, if you call to X-array, you should get an X-array data set out of it. So we're going to do that on both our reference data and our 2024 July data, and then calculate a climatology with EarthKit transforms. So EarthKit transforms gives you very high level, very easy to use functions for calculating aggregations in space and time. So in this case, we have a nice function called earthkit.transforms.climatology.mean. So this is going to find the mean climatology of our reference period. And we can see what that looks like here. So we have our single month, which will be the month of July. In fact, you can see it's month number 7 for the entire globe. So this is now our climatology that we can use to calculate an anomaly from. And we calculate anomalies by finding the difference between our July data against our reference period. So to do that, we do earthkit.transforms.climatology.anomaly, and we simply pass our July 2024 data and our climatology, and that gives us an anomaly. In the case of HagCruity5, this data is already anomalies, so all we need to do for this example is to extract July 2024. And the easiest way to do that, given this is NetCDF data, is to convert to X-array and then do a dot cell in X-array. So we're doing HagCruity5. So we're selecting the variable that comes with a few variables here, but we're interested specifically in the temperature at surface mean. So we're doing HagCruity5.tasmean.select, and then we're selecting the specific time we're interested in, which is July 2024. And then finally, we're moving on to visualization. So we can use EarthKit plots to visualize these two data sets using the same principles. So first of all, we design what's called a style. This one is a little bit complicated because I added a bunch of colors here. These are the colors that we use for our Copernicus communications when we calculate anomalies. And then we have some levels. So we're going to go from -7 to +7. We're going to extend our color range. All that means is we're going to put arrows on the end so that we catch values that fall outside of our range. And then we're going to use this units label equals degrees C. So that's our data's in Kelvin, but because they're anomalies, Kelvin anomalies are the same as Celsius anomalies. So EarthKit plots does have some very powerful unit conversion logic built in. So if I were to put units equals Celsius, it would actually try and convert the Kelvin to Celsius, which we don't want it to do because these are anomalies, and Kelvin anomalies are equivalent to Celsius anomalies. And then finally, we can plot the two data sets side by side. So we are using CartoPy to define our projections. In this case, it's just doing a Robinson projection because it's a particularly nice projection for this kind of visualization. And then we are plotting both the HagCruity5 July anomaly with the ERA5 July anomaly, and we're passing our style that we defined above to that call. And then adding coastlines and borders, adding a legend. If you haven't used EarthKit plots before, you might notice we do some of these templating strings in our labels. You can do that in legends, you can do it in titles. You'll see it again here with time. And that is extracting metadata directly from the data that you're visualizing and putting it into the title. So that means you can more easily reuse this code with some other data, and all of your labels will update to actually reflect the data that you're plotting. So you don't have to keep on redefining your titles and labels every time you plot some new data. And then, yeah, finally adding a bit of shading. Won't go into too much detail about how we do that, but it's just using some basic standard matplotlib functionality. But then we get this nice result where we can see the Hagruti 5 anomalies against ERA 5. So you can see there's a lot of similarities between the two. Obviously, Hagruti 5 is much coarser resolution than ERA 5, with some gaps of missing data as well, which you can see from where we added the hatches. But if you're familiar with Matplotlib and CartaPy, hopefully you can see that there is a significant reduction in the amount of code you have to write in order to plot these two data sets. And we also pass them both to the plotting function without, and it treated them both the same, despite the fact that one comes from NetCDF and one comes from GRIB. So nowhere in this example did it really matter that either of those data sets came from a specific file format. We followed the same approach for each. And then there were some exercises in that notebook, so I don't know if anyone managed to get to the bottom of this notebook to try and run these exercises. I won't go into too much detail here, but one of them was to choose a different month in the year. So simply went to the CDS and got a different month. In this case, it was January 2025. And the same from Hagruti 5. And again, you can see a nice comparison between the two and different areas where there's missing data from Hagruti 5, which is very interesting. And then finally, there was an exercise to do a zoomed in version over Europe. So all you actually had to do in this case was change the CRS equals Robinson to domain equals Europe. And then you get a nice European view of this. There are lots of built-in domains in EarthKit plots. So country names work. You can do things like you could say domain equals France and you would get France. There are lots of named domains like Europe is one of them. So continents also work. So yeah, you can experiment with that yourself. Try running this notebook and try and look at the temperature anomalies over an area that's of interest to you. So that's that notebook. I appreciate that was a lot of information, very, very fast. So I really recommend you take a look at that one in detail and go through it step by step because there is a lot going on there. I did my best to summarize, but maybe summarize too much.
Thanks, James. And just to clarify, these notebooks are available beyond this training course as well?
Yes, yeah, they're fully open source and available on GitHub.
Right. And they can be shared with colleagues and others as well?
Absolutely, yeah. They're in a publicly accessible repository, so yeah, available for anyone.
Great, good to know. Any comments or questions on this one? So, thumbs up. I don't see any, so I don't know if you want to go through quickly another.
We can do, yeah. Are there any in particular that anyone would like to see? Or maybe Sandor, would you like to do one? Or we could do the whatever people like to see.
Yeah, I don't know. I can do one.
Yeah.
Yeah. Okay. So let's share.
Yeah.
Okay, so I just go through the meteor computation notebook very quickly. Just a moment. Yeah, so this notebook is kind of showcasing how to use EarthKit Meteor that Iain already introduced. So we click on this link, we go to the site EarthKit Meteor, and in the API reference you can see the modules that currently we have in EarthKit Meteor. And if you, let's say, click in thermo, you see all the thermodynamic computations we added. So if you are familiar with Matthew, roughly you should see the same here. There's more to add, but it's already a nice collection of various routines which are working nicely together. So just go back to the notebook and focus on the data. So the data we get is the GRIB data, which is loaded with EarthKit data. And you see the source is a sample. So a sample is a set of files which we store in a dedicated download server for quick access. And we have recently changed the server. So you need to use the latest EarthKit data version to get the sample, because otherwise it will try to use the old host. But this is a newly generated file for this course, so it won't work. I think some of you might find this problem. So what you get here back is a grip data, which is represented as a field list with the head command, or you can use the ls. We just list the contents, only the first 6 fields in it, and you can see that it's containing on pressure levels, temperature, specific humidity, UNV, wind component data. So that's what we have. And in the first, the third chapter, we use this data, the temperature from this data, to compute the potential temperature. So EarthKit Meteo is still work in progress and currently only support array input and output. And in order to deal with grip data, we need to go to a lower level. Basically, we need to write a loop. As you see, in the cell, with the cell command, we select only the temperature fields from the input field list. And in the for loop, we go through each field. And then inside the loop, first we need to extract the pressure and the temperature, because potential temperature takes these 2 parameters. So the pressure is a metadata, which is the level actually, and we need to multiply by 100 to get it in pascals, which EarthKit Meteo takes. And then we have the temperature values as a NumPy array with the values property from the field. So then we have this pressure value and the NumPy array for the temperature, and then we call thermo.potential temperature, which is computing the resulting potential temperature. Again, the result is an array. We print it just for verification purposes, to see that the debugging purposes, just to see if it's going well. And now we want to write it back to grip, because that's the target we want. So first we need to create a new grip metadata object. So we take the existing metadata from the input temperature field, and we change the short name in it. We know, okay, you have to know it. You have to set the short name to PT, which is potential temperature in EC codes. And then we have a new metadata object, and then we create a new field out of the computed values and the metadata. And in the end, we collect these into a list, and we create with the field list from fields method a new grip field list. So if we call ls on it, we see that it looks okay. So the short name is correctly potential temperature, and everything else is taken correctly from the input temperature fields. EarthKit data offers you a kind of target framework to write data into various targets. A target can be a file on disk, an FDB, for example, and we plan to add more in the future. Currently, we write this data into a disk, because the way we generate it is in memory. And with the toTarget method, you can specify the file you want to write it. You write, and then once it's done, we read it back with from source and see if it was correctly written, and it seems to be okay. But the real verification, of course, the real proof is that we try to plot what we computed. So the next cell is showing how you can plot together the input temperature on 850 hectopascals and the resulted potential temperature field, and they all look fine. So next example is doing the same. This is very similar exercise is using the UNV wind component and computing the wind speed. It goes exactly in the same way. The difficulty now that you need to deal with 2 fields, the UNV wind component separately, but the concept is very much the same. I just quickly go through it. We plot the computed wind speed with the wind arrows, and everything looks perfectly matching. In the exercise, what I said was here to compute the relative humidity from the temperature and specific humidity fields in the input. And again, it goes very similarly to the computations I just introduced you, but now we need to handle 2 fields together, 2 field lists together, the temperature and the specific humidity fields together. Otherwise, again, it's a very, very similar computation, which is calling this very long function named relative humidity from specific humidity in EarthKit Meteo, computing the relative humidity, writing the results into a new grid field, field by field, and creating a new field list in the end, which we list. And we see that the short name is set to R, which is relative humidity, and the plot kind of looks okay. So that was this notebook. Are there any questions about